Hello and welcome back to Calculus 2, section 7.3 on hyperbolic functions. So these are the new functions you haven't discussed and seen before. These functions remind of trig. They are not trig. So I am going to start with this statement written in blood, that this section has nothing to do with trig. These functions are not periodic. So, hyperbolic functions are not periodic and have nothing to do with trig functions. The issue is that they are very similar and the confusion is there, but then you clear that confusion by studying these concepts very carefully. So I'm going to go 300 years back in time when the hyperbolic functions were defined by one of the gods of mathematics, Leonhard Euler, who was the most productive mathematician of all time. If you want his collected works, it's going to be 72 books that cost about $11,000. It's called Opera Omnia. He is the most productive mathematician of all time who contributed a lot to geometry and calculus, created complex analysis, and that the letter E, is after his name, Euler, which is spelled with E. He is the father of exponential, logarithmic, most of the trig stuff, and the hyperbolic world, and then after that you have another 72 books of stuff that he did. The most productive mathematician who for the entire lifetime was pumping 1 to 2 papers a week, and for the most of his career he was blind, so he would dictate mathematics as he was working it out in his head to people sitting around the table. So at one point in life he wrote that the sine x, the trigonometric function sine x, is e to the ix minus e to the minus ix divided by 2I, where this I is the square root of -1, the complex number, right, the imaginary number I. And he also wrote down that the cosine x is e to the ix plus e to the negative ix divided by 2. No I on this one. Called the mathematics of the time, and then adding all of these other functions and all of these other features that he worked out. So on one day, he probably said to himself, well, I have this structure over here. What if I remove i's? What if I just write the same things, same type of definition, literally just delete i's? And in his brilliant mind, he worked out all of the algebra in terms of, what would happen with identities and all these kind of things. And he found that it was very, very interesting, that it resembles the trig without actually being the trig, without having periodicity. So it was kind of completely new world. And from that point on, hyperbolic functions were born. They were connected to hyperbolas, where sines and cosines are connected to ellipses. This is not the time for you to learn this yet, but chapter 12 is coming, and those of you who go to Calculus 3, you will know that you can write the equation of the circle using trig as well. You can write the equation of the circle using sine and cosine. You can write the equation of the ellipse using sine and cosine. And it will be very simple and beautiful, but again, we'll wait for chapter 12. So now, if you remove these i's, you get the definition which says, and he called those sine hyperbolic and cosine hyperbolic because, again, it was resembling the definitions for sine and cosine in terms of ease, because you're removing I, clearly it's not the same. And then they were connected to hyperbolas geometrically, geometry-wise. You have some of that geometry presented in your book. And the word coined, right, hyperbolic functions, and then you get sine. However, you are going to have another 4 for a total of 6, right? Because hyperbolic functions resemble trig functions without being trig functions. Just the properties in terms of ease. So you're going to have your tangent hyperbolic x to be defined as the sine hyperbolic x over cosine hyperbolic x, which is, when you cancel the 2's, ex minus e to the minus x divided by e to the x plus e to the minus x. Tangent so cotangent hyperbolic x is going to be cosine hyperbolic x over sine hyperbolic x, and then you get to flip the e's. So put plus on the top and minus on the bottom. We also have secant and cosecant working the same way as they would in trig, except no i's. So the secant hyperbolic x is going to be 1 over cosine hyperbolic x, which gives us 2 over e to the x plus e to the minus x. And finally, cosecant hyperbolic x is 1 over sine hyperbolic x to give us 2 over e to the x minus e to the minus x for this one. Now I'm going to box these ones as well, because these are the other 4. But the top 2, sine hyperbolic and cosine hyperbolic, are bosses. Okay? And we use them for 99% of the stuff we're going to do. The other 1% is going to be occupied by secant hyperbolic, tangent hyperbolic pair. But that's later on for integration and a whole bunch of other stuff. So this is it. We have the definitions. And now we are going to first consider these as functions before we go and do any calculus. So now we are going to work out pre-calculus of these definitions. And the first order of business for us is to take a look at the graphs for these 6 functions and realize that those graphs are not periodic graphs. And one more time, solidify this idea that this is not the trig, even though the names kind of sound triggish, right? Because you have secant and tangent and all these kind of things. They're all secant hyperbolic x, and that word hyperbolic immediately kills off the periodicity and trig in it. So hyperbolic functions, graphs, I typed that in Google. If you use Bing, by all means. And I'm just going to go to the very first image over here and show you the graphs of all 6 hyperbolic functions. So as you can see, all 6 graphs, nothing repeats. Therefore, they're not periodic and have nothing to do with trig.
But it looks like
Sine is a wave, and that looks like x cubed over there. And the cosine hyperbolic looks like x squared, where the cosine is another wave, right, for trig. The tangent hyperbolic should stand up, but it's flat over there. And yeah.
It's like all the trig functions got drunk.
So if you take a look, the fourth one and the 6th one over there look like 1 over x without being 1 over x. The one in the middle is the bell-shaped curve, right? And you are going to see some of the statistical functions, if you ever go into the more advanced mathematics for probability and statistics, you are going to find some of the functions being given, because it's easier to deal with secant hyperbolic in terms of calculations than with the e to the negative x squared, which is actually what the model is. You can't integrate that one. You can, but... All right, so looking at these, guys, what are the basic specs of any function or every function you learned so far? You want to know domain, you want to know the range, you want to know the x-intercepts, you want to know the asymptotes, right? So those are the basic specs of any function that you have. And right off the bat, you know that the domain is all the x values you can use. So you can see that for all of these functions, domain is from negative infinity to positive infinity, and then there are some exceptions here with the cotangent hyperbolic and the cosecant hyperbolic. You can't put 0 and, some of these, because anytime when you have the sine hyperbolic in denominator, you have 1 minus 1, because when you have e to the 0 is 1. So if you have sine hyperbolic in denominator, for instance, cosecant hyperbolic x is 2 divided by e to the x minus e to the minus x, right? So when x is equal to 0, then you have 1 minus 1, and that makes it 2 over 0, which means there is a vertical asymptote. So cotangent and cosecant hyperbolic, they have asymptote at x equals 0, and that would interrupt the domain. Otherwise, domain is from negative infinity to positive infinity, right? Also, the range now, you see that the range is, for some of these, restricted, unrestricted for others. So you have pictures 1, 4, and 1, 4, and 6 have unbounded negative infinity to positive infinity with some interruptions, right? So if you are to pick any of these graphs, you should be able to just look at them and come up with these. Now, when you are observing the interesting features, clearly the most interesting ones are the ones in the middle. So the one for the cosine hyperbolic that looks like x squared, it's not an x squared, not even close, right? When you take any kind of a rope or a chain or a cord or whatever, and you pin it to 2 points, the natural sag given by gravity is going to be modeled by cosine hyperbolic, not by x squared. Yes?
Was that just a coincidence that happened to be?
Yeah, well, look, mathematics is developed to model the world around us, right? It will be the same as asking, is it just coincidence that exponential function models decay, right? So you have mathematics that you develop, and then you find that it resembles the world, right? And then it becomes a mathematical model. So when you hang a chain or a cable or those power lines and phone lines, they will form this type of a graph. And then you take the points, you do the curve fitting, and it will tell you, the specs around the other constant numbers. So it is the function that models the chord, and it's important to have that because let's talk about the power line going over the highway, right? Think about it, and I mean you have thousands of those examples. As soon as you start, driving back home, you will see how many times the power lines go over the highway you're on. So if you stretch it from one tower to another tower, let's say there is tension there's no sag at all, would that be something good or bad? Well, let me ask you a question. What happens when you have the winter, it's extremely cold? What happens in the extreme cold with all objects? They constrict, they shrink. So if the wire is stretched flat between the two towers and it starts shrinking, right, because it's cold, you have two possible outcomes. outcome number one, it snaps. Outcome number two, it rips the tower out of the ground, right, and doesn't snap. There's no third outcome on that particular scenario. Now, can you just say, put the, whatever sag there, just to make sure that when it, can you? Well, what happens in the summer now? And in the summer, consumption of electricity goes up because everyone turns on air conditioning because everyone is trying to achieve negative 20 in the house for whatever reason. So there is high consumption, which higher currents, higher temperature. I did mention that already once. Plus the temperature of the environment, meaning it's summer, it's hot. What happens with objects when they are exposed to the heat? They expand. So that sag is going to be even bigger now, right? So electrical engineers, power engineers, right? They have to compute the sag using this function very carefully so that in the summer it doesn't go too low for trucks to hit the wires, right? And it has to be just perfect, right? Because in the winter it can stretch, right, and then either break or rip out the tower. By the way, one of those big towers for, let's say, 100 kilovolt level or more, with a set of wires on one side, right? Each tower owns the set of wires on its side, and the next tower with a set of tires on that side, right? 100K. What? So you play the game, and you put 10 of those, it's $1 million, all right? And then you see them like going miles and miles and miles. It's very expensive stuff, right? So you don't play with these things, right? They have to be carefully computed. So now you see there is a function that computes this, and we are going to have one of the homework exercises that will ask us to compute some of these values. So the other stuff that you can compute, obviously, x and y intercepts. You see x and y intercept for sine are both 0 and 0. The tangent hyperbolic 0, 0. Cosine hyperbolic has no x-intercept, does have a y-intercept at 1. No x-intercepts on cotangent hyperbolic and cosecant hyperbolic. And then there is another intercept at 1 for secant hyperbolic. That will be a y-intercept for that bell-shaped curve. So all of the features that you learn, that you should be able to look at the graph and tell. So maybe you want to list the features down so you know when you bring this picture on Google or flip the book open, it would say what? It would say, what are the domain, range, x-intercept, y-intercept, and asymptotes, meaning horizontal, vertical asymptotes. So look at graphs to get number 1, domain and range. Number 2, we want to know x and y intercepts. And finally, number 3, horizontal and / or vertical asymptotes. Oh, you can't see what I'm writing. It's not like it will up. Oh, wow, it's there. Thought we have to wait 15 minutes for each one of these to show up. So look at the graphs, and I can give an example immediately of this. Let's go with as I said, the most important graph of all 6 is a cosine hyperbolic one. That's the most important, followed by secant hyperbolic one, followed by sine, and then the other 3 on a pile. Now, the most important graphs, calculus-wise, not graphs, functions calculus-wise are sine and cosine because they give birth to everything else. So if I'm going to take a look at y equal cosine hyperbolic x and I take a look at the graph, going through 1 over here, I will go and say domain is going to be from negative infinity to positive infinity. Range is going to be including 1 to positive infinity, excluding, right? X-intercept, none. Y-intercept at 0, 1. Vertical asymptote, none. Horizontal asymptote, none. Just by looking at the graph, right? You have these 6 pieces on, and you should be able to, if I provide you with the graph, you should be able to state this for all 6 functions. I gave you the graph, you looked at right, you look at the graph, write the specs. So that would be graphing. That would be pre-calculus kind of thing. And you know what? Now we can actually go and figure out some identities for hyperbolic functions, because they resemble trig without actually being trig, and they have the identities. Now, identities, I understand, are going to be really annoying because they're close to trig. The functions are, the identities are swapped, and it's really close without being what you want it to be. So some of the problems on the exam could be just prove the identity, blah, 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 in which case you will change everything to ease and then grind through algebra. So I'm going to pull up the properties, and then we'll do a couple of examples of that. And that will end the pre-calculus part. We can start derivatives and integrals. Please no puzzle, please no, but thank you. This is really stressful, because you never know when the puzzle is going to come up. Pick all traffic stops. One student told me that even if you always have 9 pictures, even if you have 5 of what they're looking for, they're only looking to click at least 3. I'm afraid to test that, because I'm have to do it again, another one, but maybe one day. It hasn't been popping up lately, so I'm happy. Okay, so now we are going to take a look at hyperbolic identities, and I will kind of need you to keep your trig identities also like in the back of your mind, just to see how similar, annoyingly similar these are, right, and how easy it is to confuse them, which means that you should have hyperbolic functions listed so you can see them all, and trig functions listed, identities listed to see them all and see how they work together. So hyperbolic identities. So we start with number 1, cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. So cosine hyperbolic squared minus sine hyperbolic squared is 1. Yeah, you remember sine squared plus cosine squared equals 1, right?
Uh-huh.
Well, but do you remember what the cosine squared minus sine squared was? Close, double. So cosine squared minus sine squared in trig gives you cosine 2x. I know. But just to make it worse over here, the sine squared hyperbolic plus cosine squared hyperbolic will give you cosine hyperbolic 2x. So the results of two formulas are completely swapped. So I know that's what happened. It has to happen because remember what we did. Removed I. Use the same definition, removed I. You are removing a multiplier of square root of -1. In some cases, when you square it, it just plays the role of what's I squared? It's -1, right? So obviously, it's just going to throw off formulas just a little bit. You can't throw it off a lot. All right, let's go with the next one. 1 minus tangent hyperbolic squared x is equal to secant hyperbolic squared x. Usually, this is where students start cursing and filling up the swear jar for the food. Cosine hyperbolic of x plus y, sum of two angles. So for the cosine, they used to change the sign. So if there was a plus here, it would be a minus in the formula. And if it's minus, there will be plus in the formula. Well, these keep the same sign. So you have cosine hyperbolic x, cosine hyperbolic y, plus sine hyperbolic x, sine hyperbolic y. 5 sine hyperbolic of x plus y is going to work exactly the same as trig, actually. So you have sine hyperbolic x, cosine hyperbolic y, plus cosine hyperbolic x, sine hyperbolic y. Number 6, there it is. Cosine hyperbolic 2x is sine hyperbolic squared x plus cosine hyperbolic squared x. So between 6 and 1, right? Sine squared plus cosine squared equals 1. And then cosine squared minus sine squared equals cosine 2x. So those two formulas are completely swapped. They're answers. Then we get to the sine hyperbolic 2x, which is exactly the same as in trig. 2 sine hyperbolic x cosine hyperbolic x. That's identical. Number 8 and number 9, these are the power reducing formulas. When you start integrating, the same rules go, right? You have to use power reducing if you end up with a sine square, hyperbolic square, or cosine hyperbolic square. So cosine hyperbolic squared x is going to be cosine hyperbolic 2x plus 1 over 2. And number 9, sine hyperbolic squared x is going to be cosine hyperbolic 2x minus 1 over 2. For your trig, we had 1 first and then cosines. So it was 1 plus cosine 2x and 1 minus cosine 2x. Over here it's reversed. It's cosine first and then 1s. So gotta be careful with that. And the last 3 functions, I'm just gonna call all 3 of them 10. Even and odd. So cosine, we see that on a graph. So cosine was even. Sine hyperbolic was odd. And tangent is also odd. Tangent hyperbolic. There we go. So these are additional 12 formulas. So right now we are at 18 formulas plus 6 graphs. What should be happening about 50 in this section? So now the question on the exam is prove number 6, prove number 3, prove number 9, prove number blah. So let's work out some of these examples, and then we're going to pick up something from homework and do another. So which example should I work up in class over here? Number what?
I like number 6.
Number 6. Excellent. I hate you. Prove number 6. So what's number 6? Number 6 says that the cosine hyperbolic of 2x is equal to cosine hyperbolic. So a little bit of algebra, right? There is nothing you can do on the left-hand side, so just copy that one. Exponents are 2x because the argument of the cosine was 2x, so whatever is there you copy. On the right-hand side, I have e to the 2x plus 2e to the x, e to the minus x, and then plus e to the negative 2x over 4, because it's a common denominator. I mean, 2 squared is 4, minus, then you have another over 4 as e to the 2x minus minus 2 e to the x, e to the negative x, plus e to the negative 2x. So when you square these, we use the basic algebra. There, now you see that these guys are the same and they drop. So what you have on the left side is e to the 2x plus e to the negative 2x over 2. And on the right-hand side, guys, I have the formula backwards. This formula is supposed to say plus over there on top. So it's plus in between these. Holy nightmare. It's a plus, plus, and a plus. So now e to the 2x plus e to the 2x is 2e to the 2x plus 2e to the negative 2x over 4. And then when you cancel the factor out 2 and cancel with the 4, you get e to the 2x plus e to the negative 2x over 2 is the same as e to the 2x plus e to the negative 2x over 2. So left side equals the right side. So all you need to do is to convert everything you see into e's, and then just follow the algebra, follow calculations down to prove this. So I'll give you the cheap one to try from homework, then we can try one of the spicier cases, and then we can start calculus. So here's the cosine hyperbolic x plus sine hyperbolic x is equal to e to the x. So try that one.